Hey everyone, welcome back to Abstract Algebra 1. This will be part B of Lecture 7. So we just finished writing a proof of a theorem that basically said that if I've got a pair of cycles, so given a pair of disjoint cycles, alpha and beta, alpha beta equals beta alpha. I'm paraphrasing, but that's more or less what the theorem said. Right? And we wrote a proof of this, and it was very straightforward and easy to see. Let's talk about it. So what does this actually say? It just basically says that if cycles are disjoint, right? If I have two cycles that don't have common elements that they operate on, then the order doesn't matter. Now, the implication isn't necessarily that if I have a pair of non-disjoint cycles that they don't commute, but it's just saying that in general they may, right? Okay, so let's talk about an example next. So let's start with a non-disjoint cycle. So given a non-disjoint cycle, I'm going to write this down. So 1, 3, and then as a cycle, and then 2, 7 as a cycle, and then 4, 5, 6 as a cycle, and then 8 as a cycle, and then 1, 2, 3, 7 as a cycle, 6, 4, 8 as a cycle, and 5. So we can take this cycle, or this collection of cycles, this permutation, and we could write it as a disjoint cycle. All right, let's make sure that we know how to do that. So this is equal to, starting with just 1 goes to 2, which goes to 7. 7 goes to 1, which goes to 3. 3 goes to 7, which goes to 2. 2 goes to 3, which goes to 1, right? So that cycle closes there. So 1, 2, 3, let's put on the 4 next. All right, what happens with 4? 4 goes to 8, 8 is fixed. And then what happens with 8? 8 goes to 6, and 6 goes to 4. So that cycle closes there. And then how about 5? 5 is fixed here, and then 5 goes to 6. And then 6 goes to 4, and 4 goes to 5, so it closes. Okay, so 1, 7, 3, 2, 4, 8, 5, 6. So in addition to just being efficient and economic, this disjoint notation adds the advantage of, it has a really great advantage. It has the advantage of being able to easily identify the order of the element of the permutation by sight. We can identify the order of an element, in this case a permutation, by sight when it is in cycle notation. Right, so mathematicians will always tend to favor the most simplistic notation, and it's always a perk, an advantage, when in addition to just being more simplistic, you also can identify a key characteristic from the notation itself. Okay, and so this next theorem works on this idea. The order of a permutation of a finite set written in disjoint cycle form is the least common multiple of the lengths of the cycles. All right. Okay, so that's interesting. So let's see some examples here. What do we mean by this? Well, if we let alpha equal 2, 3, 1, 5, and then 4, 6, right? And so this is going to be a permutation of in S6, right? Well, the order, what is the order of alpha? What is the order? Right, what does the order mean? Remember what the order means. How many times do you have to perform the operation to get back to the identity? What's the order of alpha? Well, the idea here is if I look at this and I can see that this cycle has 4 elements in it, this cycle has 2 elements in it, then the order of alpha, supposed according to the previous theorem, is the least common multiple of 4 and 2, which is 4. Okay. So, according to this theorem, if I apply this permutation to itself 4 times, I will arrive at the identity. So let's see that. Let's see if that happens. So alpha to the 4th is 2, 3, 1, 5, 4, 6. There's one of them. 2, 3, 1, 5, 4, 6. 2, 3, 1, 5, 4, 6. 2, 3, 1, 5, 4, 6. Right. So you've got the 1, 2, 3, 4. Right, so let's see what happens. What happens with 1? Well, remember you start at the right and you move kind of left. So 1 goes to 5, 5 goes to 2, 2 goes to 3, 3 goes to 1. Okay, 1 stays fixed. What about 2? 2 goes to 3, 3 goes to 1, 1 goes to 5, 5 goes to 2. What about the 3? You can see what's going to happen here. 3 goes to 1, 1 goes to 5, 5 goes to 2, 2 goes to 3. So you can see the same thing will happen with 5. What happens with 4? Well, 4 goes to 6, 6 goes to 4, 4 goes to 6, 6 goes to 4. So it fixes it. What about 6? 6 goes to 4, 4 goes to 6, 6 goes to 4, 4 goes to 6. So it fixes it. Okay, so the identity here is, it's obvious that this is going to work, right? Because this guy needs to move 4 places. This guy needs to move 4 places. He needs to move 4 places. He needs to move 4 places, right? So I'm going to have to do it 4 times to get these guys home. These two, they only really need to move 2 places. But I have to move these guys 4 places, so that means I have to move these guys 4 places, which just means they'll cycle through twice, right? 6 goes to 4, 4 goes to 6, 6 goes to 4, 4 goes to 6, right? It kind of repeats itself twice. So that's where the least common multiple comes in, right? If I did it 5 times, that would be too few. If I did it 2 times, these guys will go home, but these guys would only be halfway through their cycle. So I have to do it 4 times. So in a lot of ways, this is it's kind of obvious. I don't think we need to worry about the proof. But you can see how you would prove it, right? You can see the principle here, right? It's all a multiples game, right? This guy has to move 4 places to get back. These guys have to move 2. So I have to do some multiple of 4 and 2. The least common multiple would be the lowest number, which is the definition of the order. Okay, excellent. All right, next. Okay, so now we've got that idea down. Let's talk about this next theorem. Okay, every permutation in Sn, every permutation in Sn, and here n needs to be greater than 1. Every permutation in Sn, n greater than 1, is a product of 2 cycles. This one may throw you for a moment. Okay, this one could throw you for a moment. So what this is basically saying, What's the idea here? So if I have 1, 2, 3, 4, 5, what this is saying is there's a way to write this permutation using just some product of 2 cycles. You know, whatever they happen to be. 1, 5, 1, 4, 1, 3, 1, 2, for example. Okay. Does this one work? Well, let's see here. So if I start with 1, 1 goes to 2, okay? What happens to 2? 2 goes to 1, 1 goes to 3. What happens with 3? 3 goes to 1, 1 goes to 4. Okay, what happens with 4? 4 goes to 1, 1 goes to 5. It's true. Right? So in this case, 1, 2, 3, 4, 5, the permutation can be written as a product of 4 2 cycles. So without the commas, you'd write this 1, 5, 1, 4, 1, 3, 1, 2. Turns out there are other 4 cycles which can be used as well. Right? Another example, you could write it like this: 5, 1, 5, 2, 5, 3, 5, 4. Right, let's see how this works. Starting with 1, what happens to 1? 1 goes to 5. Wait, 1 second, I think I did it wrong. Yep, I did it wrong, sorry about that. I got ahead of myself. 5, 4, 5, 3, 5, 2, 5, 1. It's got to cycle in the right direction. So what happens with 1? 1 goes to 5, 5 goes to 2. What happens to 2? 2 goes to 5, 5 goes to 3. What happens with 3? 3 goes to 5, 5 goes to 4. And what happens to 5? 5 goes to 1. 4 goes to 5. 5 goes to 1. Right? So you see it wraps right around there. All right, so here are two ways to write this simple cycle as a product of 2 cycles. Now what this theorem is saying is that every permutation in Sn, no matter if it's a simple one like this or a crazy one, they can all be written as the product of 2 cycles. Okay. All right. Well, let's see how that works. Let's prove that. Let's write a quick proof here. Okay. So we want to start by noting that the identity. Right. Now this is kind of the tricky part here. Note that the identity can be expressed as 1, 2, 1, 2. Okay. Right. So it's the product of 2 cycles. Right. So it can be written like this. The product of 2 cycles. All right. By the previous theorem, right, we know that every permutation can be written as a product of disjoint cycles. By the previous theorem, we know that every permutation can be written as the product of disjoint cycles. Right, so we're going to need that. So given that, we'll write our candidate permutation as a product of disjoint cycles. We'll have A1, A2, ... AK, and then B1, B2, BT, and then we'll say C1, C2, CS, right? So we've got just a candidate here. Okay. And a simple kind of calculation can show you that if for the A's here, you basically take the ending point and map it up successively with the character on the other end of the array. So A1 and AK, oops, sorry. So A1 and AK, and then A1 and AK minus 1, A1, and then eventually K minus 1, K minus 2, and then you'll get up to 3, 2, right? Like this. So this piece here would map like that. These are all 2 cycles, obviously, right? One, and it's just got 2 elements in them. The same thing can be done with the B's. B1, BT, B1, BT minus 1, B1, B2, and then the same thing. And so that's this piece here. And then the same thing for the C's. C1, CS, C1, CS minus 1, C1, C2. Okay, and this is a product of 2 cycles. Right, and so is a little hand waving there. But you can test this out. Try this with, you can use a smaller kind of induction argument on this. But this is basically the form that the proof will take. You can always take this and just unwind it like this. So the first and the last, pull it apart. The first and the second to the last, pull it out. First and the third to the last, dot, 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 first and the second. For each of the cycles. Right, and because these are disjoint, you know that none of these elements are ever going to be here or here, right? So this kind of a structure always works. Always works. Let's try an example or 2 of this, just to see how we can kind of quickly write these things. So we saw the 1, 2, 3, 4, 5. What about something more complicated like 1, 6, 3, 2, and 4, 5, 7? Well, just starting with this first cycle here, I'll take the 1 and the 2, and then I'll take the 1 and the 3, and then I'll take the 1 and the 6. That breaks this cycle down into 2 cycles. Then over here I'll take the 4 and the 7, and then the 4 and the 5. Now, did this work? Better check. Let's see if we can recreate this cycle by making this disjoint. Right now it's no longer disjoint, but it's written as 2 cycles. Let's make it disjoint. So we start with the 1, right? Starting at this side, 1 goes to 6. Okay, what happens with 6? 6 goes to 1. 1 goes to 3. Okay, what happens with 3? 3 goes to 1. 1 goes to 2. Okay, what happens with the 2? 2 goes to 1. Right, so it wraps back around, cycle closes. So we've got 1, 2, 3. Let's put in a 4. Okay, so 4 goes to 5. Okay, that's that. 5 goes to 4. 4 goes to 7. Okay, what happens with 7? 7 comes in, goes to 4. Wraps back around, closes, right? So these are the same. So you get the same, it's the same permutation, just written in a different way. All right, very cool, very cool. Okay, and we could do this, right? You can just make up permutations. So let's say 1, 3, 5, and then 2, 4, 6. All right, so 1 goes to 5, 1 goes to 3, 1 goes to 5, 1 goes to 3, and then 2 goes to 6, 2 goes to 4. Okay, does that one work? Well, let's see. 1 comes in, it goes to 1 goes to 3, 3 comes in, 3 goes to 1, 1 goes to 5. Okay, and then in comes the 2, 2 goes to 4, 4 goes to 2, 2 goes to 6, and 6 goes back to 2. So you get it back. Right, so it's just this kind of thing about hopping kind of from thing to thing, right? It's very nice. You could also reverse it, which we'll see in a moment. We'll see that in a moment. All right, so these are 2 cycles, right? Now, one of the things you'll notice here is, like, for example, up here, this 1, 6, 3, 2, 4, 5, 7 produced a list of 2 cycles, and I've already said that there are more than one way to write these things, to break these things down. We saw an example of that. But the one thing that's preserved when you break these down into 2 cycles, not necessarily the order, not necessarily the breakdown itself, right? The pairs, they'll vary. But one thing that is constant is the evenness or the oddness of the number of 2 cycles. So here I've got 1, 2, 3, 4, 5. So this is odd. Right, another example I could do here would be 2, 1, 2, 6, 2, 3, 7, 4, 7, 5. That'd be 5 of them. Again, another odd. Right, down here, when I do this breakdown, I get 1, 2, 3, 4 of them. So this has an even number of 2 cycles in it. Right, this evenness and oddness is the subject of the next theorem. Right, kind of a profound thing about permutation groups. So theorem. If a permutation alpha can be expressed as a product if a permutation alpha can be expressed as a product of an even number of 2 cycles, then every decomposition of alpha into a product of 2 cycles must have an even number. Okay. Then every decomposition of alpha into 2 cycles will have an even number. Right? So here, for example, let's do this one. So here, for example, I was able to decompose this permutation into a product of 2 cycles. 1, 2, 3, 4 of them. So what that means is that there's no way for me to break this permutation down into 2 cycles where there's an odd number, like 5 or 7 of them, or 3. It's always going to be even. Okay. Now, a little further here, what we can say in general, if alpha is equal to beta 1, beta 2, ... beta r, and alpha is equal to gamma 1, gamma 2, ... gamma s, right? Now, what are these? So the betas and gammas are 2 cycles, where the betas and gammas are 2 cycles, right? So if I can take this permutation and break it down into different 2 cycles like this, then R and S may not be equal, but R and S are both even or both odd. Then R and S are both even or both odd. Okay? And so this is where we get the idea of an even permutation or an odd permutation. All right? So let's see some examples of how this works. Okay, let's take our familiar 1, 2, 3, 4, 5 and break it down a couple of different ways. 1, 2, 3, 4, 5. Okay, so this is our familiar one. And so we saw that we can break it down like this: 1, 5, 1, 4, 1, 3, 1, 2. Right? And there are 4 of them here. Even number of them. We also saw this one: 1, 2, 3, 4, 5. And we saw where we could go 5, 4, 5, 3, 5, 2, 5, 1. And obviously here is another one with 4s. Right, now there are going to be more of these. There are more options. Right? One other one to look at is maybe this one. They become a little more complex, tricky to figure out. But we could go like this: 5, 4, 5, 2, 2, 1, 2, 5, and then 2, 3, 1, 3. Right, and obviously there's 6 of them here. Now, does this one even work? Well, let's see here. 1 goes to 3, 3 goes to 2. 2 comes in, 2 goes to 3, 2 goes to 3. There it is. 3 comes in, 3 goes to 1, 1 goes to 2, 2 goes to 5, 5 goes to 4. 4 comes in, 4 goes to 5. So it does work. Right, but the key here, the point, is that here's 4, here's 4, here's 6. So if they're not always the same number, right, you can make these things needlessly complex if you want to. Right, but the point is that there's never going to be a string of 2 cycles of length 5, because this is an even permutation. This is an even permutation. Okay, let's see an example of an odd permutation. 1, 6, 3, 2. This is one we already saw. 1, 6, 3, 2, 4, 5, 7. Okay, we saw that this could be written as 1, 2, 1, 3, 1, 6, and then 4, 7, 4, 5. Right, that's one way to do it, and you can see 1, 2, 3, 4, 5 of them. Right, another way to do this would be, you could write this as also as 2, 3, 2, 6, 2, 1, and then 7, 5, 7, 4. Right, and this is also a 5. Right, so this is an odd permutation. So this one's odd, this one above is even. Right, so the point here also, just to emphasize, is that there's no way to break this down into a product of 4 2 cycles, or 6 2 cycles, or 2 2 cycles, or 8 2 cycles. It's always an odd number. Okay. All right, very good. Very good. So we have a definition here next then, and that's going to obviously be the definition of even and odd permutations. A permutation that can be expressed as an even number of 2 cycles can be expressed as an even number of 2 cycles is called even. Okay. A permutation that can be expressed as an odd number of 2 cycles is called odd. Okay, so I'm just going to let you fill that in. So a permutation is even or odd based on the number of 2 cycles required to express it. Okay, it turns out that, you know, every permutation is either even or odd. Okay. Okay, a nice theorem that comes off of this. Even permutations in Sn form a subgroup of Sn. Okay. So even permutations in Sn, when you combine them, you can only get other even permutations. Right? I like this. This is quite elegant. So even permutations, when combined, only produce even permutations. This is nice. This is very much like what you experience with regular arithmetic. If I take even numbers and I combine them, I add them together, I only get even numbers, right? 2 and 6 is 8 even. 10 and 22 is 32. It's even number, right? I'm always going to get an even number if I add two even numbers together. It's not the case with odd numbers, though. So 3 and 5, for example, I add them together, I get an even number. If I add an even and an odd, I'm not guaranteed to get even or odd. Okay? So this is similar to what we see when we're adding numbers in normal arithmetic. Right, so the even permutations all form a subgroup. Odd permutations do not. Odd will produce even or odd. Odd and even will produce odd. Right? So there's a nice symmetry there with regular arithmetic. Some of the most interesting things about abstract algebra, I think, are the way it dovetails with our everyday experience of regular mathematics. This is a good example of that, where evens together stay even, odds together, and the odds and evens mixed together may be odd or even, and then odds together are not odd, right? Similar to the way it works with regular arithmetic. Okay, another group. We're getting close to the end here, right? So this is the alternating group. So the group of even permutations, of n symbols is denoted by an and is called the alternating group. Of degree n. Okay, so just another another group. Now, an is obviously a subgroup of Sn, right? Right. So if I've got some set S, 1, 2, ... up to n, right? Sn is all the permutations on this set S, and an is all of the odd permutations, right? So, well, that's not accurate. I should say it like this: an is a strict subgroup of Sn. Right? It's not it's basically Sn, but just the even side of Sn, the even permutations of Sn. Now, it turns out that the an represents exactly half of Sn. It represents exactly half of Sn. That's interesting. That's kind of crazy, right? Again, mirroring what you experience with regular arithmetic. Half of the numbers are even. Half of the positive integers are even numbers. The other half are odd. When we're talking about permutation groups, it's the same idea. In Sn, half of them are even, so half of them are the alternating group. Okay, so let's see that. Let's see that proof. Let's write the theorem. So for n greater than 1, the order of an is equal to n factorial over 2. That's the theorem. An is the alternating group. All right. And what we're saying is that the size of the alternating group, an, is n factorial over 2. Well, n factorial was the size of the symmetric group, Sn. And so an being the subgroup, it represents half of Sn. All right, so that's kind of remarkable. Let's prove it. So let's let alpha be an odd permutation, right, in Sn. Okay. If alpha is odd, then 1, 2 times alpha is even. Right, that's obvious, right? Because if alpha is odd, then when I write it as 2 cycles, it'll have an odd number of 2 cycles. If I put one more on there, it's even. Okay, and 1, 2 alpha is not equal to 1, 2 beta whenever alpha is not equal to beta. Okay, so what does that mean, right? So these things together imply there are at least as many even permutations as there are odd ones. Okay, so there's at least as many even permutations as there are odd ones. Now, on the other hand, let's let alpha be even in Sn. Okay, so by the same token, if I take 1, 2 times alpha, that must be odd, right? So if alpha has an even number of 2 cycles and I put one more on it, then it becomes an odd permutation, right? And it's clear that you're not going to get the same result. 1, 2 alpha is not equal to 1, 2 beta if, or so we'll say when alpha is not equal to beta. Right? And so that implies the exact same thing as the upstairs did, right? So there are at least as many odd perms as there are even ones. Okay. Right, and so if there's at least as many evens as odds and at least as many odds as evens, well, then that means they're the same number, right? So the number of odds equals the number of evens implies that the order of an must be equal to half the order of Sn, which is 1/2 n factorial. Right, so again, a remarkable, I mean, it's super simple to see why this, it told it very simple, easy logic to follow, but kind of interesting. I mean, you maybe wouldn't have expected that to be the case, right? That the even permutations would represent exactly half of all the permutations of Sn. Okay, let's do one final example. And so for this final example, what we're going to do is we're going to break down S3 into even and odds. So as a final example, we'll consider S3, right? And so remember, S3 is the set of all permutations of 1, 2, and 3, right? Or smallish set, but that's okay. Right, and so we can write out all the permutations. So we've got the identity, which fixes everything. Right, 1 comes in, it stays. 2 comes in, it stays. 3 comes in, it stays. And then we saw this one, the 3, 1, 2. 1 comes in, it shifts over to 2. 2 comes in, it shifts over to 3. 3 comes in, it shifts back to 1. And then we had the other cycle, full cycle, which was 2, 3, 1. Okay, 1 comes in, it shifts over to 2. Wait a second, 2, 3, 1, 3, 1, 2. 2 goes to 3. I think I did that wrong. Which one? Hold on a sec. I think I wrote that down incorrectly. Yes, 2, 3, 1, 3, 1, 2. Oh no, that's fine. That's fine. Yep, that's fine. Okay, then the other one is where we fix 1 and we let 3 and 2 switch places. And then we could let 2 and 1 switch places and fix 3. And then we could fix 2, and so 1 and 3 are going to rotate around. Okay, so these are all of the elements of S3. And these can all be expressed as 2 cycles, right? So we can move these over. Now, with the identity, this one is a little weird, but it can be expressed like this: 1, 2, 2, 1, 1, 3, 3, 1. Right, now let's make sure that we understand that. So 1 comes in, 1 goes to 3, 3 goes to 1. Right, so 1 gets fixed. 2 comes in, 2 goes to 1, 1 goes to 2. Right, so 2 gets fixed. And then what happens if 3 comes in? 3 comes in, 3 goes to 1, 1 goes to 3. It gets fixed. Right, so everything is fixed here. Right, so this is also known as the identity, which I'll write as E. Now for this one, we could say 3, 2, and 3, 1. All right. Okay. And for this one, we can write 2, 1, and 2, 3. Actually, I want to write this differently. Let's write 3, 2. I think that's better. Yeah, 3, 2, and 3, 1. The order matters here, right? They're not disjoint, so they don't commute. Okay, so let's put it in that order. And then down here, these can be written as 2 cycles. Remember, when an element's fixed, you can just leave it off the cycle because it's not moving. So these are 3, 2, 2, 1, and 1, 3. Right? Now, these 3 here are all odd, right? They have 1 2 cycle. These up here are all even, right? So here we've got 4, 2, and 2, right? So the order of S3 we know is 3 factorial, which is 3 times 2 times 1, which is 6. And we can see that A3 is going to be the evens, so A3 will be the identity. It'll also be 3, 2, 3, 1. And it'll be 2, 1, 2, 3. Right? If you wanted to write this in the normal notation, you'd say that A3 is the identity, and then it's 3, 1, 2, and then it's 2, 3, 1. Right? And obviously, A3, the order of A3 is 3, which is half the order of S3. Right? So there it is. So the alternating group here is basically the top 3 elements here, and the lower 3 elements are the odd elements of S3. Okay. All right, I think we'll leave it there, and yeah, that'll be it for permutation groups for now. We may come back later in the course, but next time when we get together, we'll talk about isomorphisms. So we'll talk about isomorphisms in the context of group theory. All right, until then, take care, and we will talk to you all next time.